Thanks, everyone, for coming tonight to listen to me talking about science. I hope I will be able to entertain you. I've been introduced already. I'm from the University of Manchester in the UK. Manchester is the second largest city in the UK and has a very famous university. Rutherford was there. You might have heard of him. He split the atom, as we say. But even more importantly, it has two of the biggest football clubs, or soccer, as you would say, on the planet, Manchester United and Manchester City. And it is known for its rain. So I'll be talking about the deep underground neutrino experiment, the biggest experimental project planned here at Fermilab. And before I can introduce you to the experiment, I have to spend some time just introducing the general concept, what is a neutrino, and why are we so interested in studying it. So let me start with what all particle physicists ask, which is what are we made of? And we all know that all the matter surrounding us is made of atoms, and in the center of atoms are nuclei, and the nuclei consist of protons and neutrons, and in orbit around the nucleus are electrons. That is more or less enough to describe the majority of matter surrounding us. But for us particle physicists, we always want to go to the elementary, and if we look a little closer, what we see is that the protons and neutrons that make up the nucleus of the atom are actually not elementary and contain particles which we call quarks, and we now understand that these are indeed elementary. The difference between a proton and a neutron is just the combination of quarks they have, 2 up, 1 down, or 2 down and 1 up. Now, over the last 50 years, particle physicists have extended this family of elementary particles, and the picture you see here encapsulates our current understanding of what the fundamental particles are that make up our world. So the up and down quark are shown here. So these are the ones which make the proton neutron. But then they repeat again and again with in a second and third family of heavier quarks. Specifically here, the top quark should be mentioned at Fermilab because it was discovered at the tevatron. And then there are the leptons, here electron, and again the electron comes back as a heavy electron, which is the muon, and then again as the tau. Here are the neutrinos. These are the particles we're interested in, and they also come in 3, and what we call here flavor is indicated by this subscript, so they always come in pairs, a charged lepton and a neutral lepton. They are the particles that mediate the forces. We are aware of 4 forces: the strong force, which is mediated by a gluon; the weak force, which is mediated by heavy particles we call W and Z bosons. Perhaps the force which is most familiar to everyone, the electromagnetic force, which is mediated by the photon, and then gravity, which is actually not on here because it is too weak to be really studied by particle physicists. The neutrinos are special here because they are electrically neutral, so these we call the matter particles. They don't have electric charge, and they only feel the weak force. And of course, if they have mass, and we know they have mass, gravity. So why do we actually need the neutrino? And that goes back to, well, more than 1930s, it's 90 years ago, something like that. Time flies. Where the radioactive decay, beta decay, was discovered, and what was seen is that a nucleus transforms by emitting an electron. And the process underlying this is a neutron that decays into a proton and an electron. Now, people studied, and this is from 1935, the distribution of energy of the what they call beta rays, the electrons coming out, and they were really confused by the fact that this is a continuous spectrum, because it shouldn't be, and the fact that it is a continuous spectrum meant there was some energy missing. Now, at the time, people actually, like Bohr, for example, they were actually prepared to give up energy conservation to explain this. These days, what particle physicists always do when they don't understand something is they invent a new particle. Now, Wolfgang Pauli, an Austrian physicist who actually worked in Zurich in Switzerland, he actually did what modern particle physicists do. He invented it. He said there's just other particle must be neutral in order to conserve charge, which is emitted in this process. And he wrote a letter to a conference which he couldn't attend, and I've reproduced it here. And don't worry, I've also translated it. So he says, I've hit upon, so dear radioactive ladies and gentlemen, I've hit upon a desperate remedy. So far I don't dare to publish. So I just tell you first, dear radioactive people, with a question of how likely it is to find experimental evidence for such a particle, which he postulated would be in that, emitted in that process to fix the problem of energy conservation. So what you can see from that text is actually that Pauli wasn't entirely comfortable with this idea, and one of the reasons was that he thought there was no way we could ever realistically prove that the neutrinos exist. Now, we know now that this was correct. There is a particle emitted. This is, in this particular case, an antineutrino. And because it comes with the electron, it has this flavor, as we say, of electron neutrino. Now, actually, Pauli called it the neutron. Now, the neutron is already used the word, and then Enrico Fermi, after whom this lab is named, he then changed the name to neutrino, which is adding an Italian ending, which means like the little neutron, the little neutral one. At this point, there was one neutrino. This, what we know now, is the electron neutrino. But it was soon suspected that there would be neutrinos also corresponding to the heavier leptons. And the muon neutrino was discovered. And of course, this is the Nobel Prize, which was awarded in 1988. And I'm sure everyone here in the audience knows Leon Lederman, the former director of the lab, who actually recently passed away, who shared the Nobel Prize with Melvin Schwartz and Jack Steinberger for discovering the muon neutrino. So again, I said this before, they come in pairs. This is a property we call flavors, and there are three types of neutrinos, and in the meantime, we have discovered all three. So why is this exotic particle so important? Well, even though we don't see much of it in our everyday life, it is actually very, very abundant. And if you look anywhere in the universe, and you'll see that on average, there are 1 billion more neutrinos that are left over from the Big Bang than we have the classical, if you want, proton, neutrons, and electrons. If we looked anywhere in the universe in a box which is 1 meter times 1 meter times 1 meter, or 3 feet times 3 feet times 3 feet tall, then you would find, on average, not here, obviously, there are lots of protons here. Most of the universe, however, is empty. You would find 10 protons and 300 million neutrinos. So that makes neutrinos actually the most abundant matter particle in the universe. At any given moment, for example now, lots of neutrinos also reach us from other sources, specifically the sun. In the sun, you have fusion processes, and these fusion processes among protons, they create neutrinos, and the flux of neutrinos is gigantic. So in every second, 10 to the 11, so a number with 11 zeros, 10 to the 11 neutrinos pass through your fingertip. That you don't worry about this, or we generally don't worry about this, is just a consequence of the fact that neutrinos don't do very much. They don't interact very often and only feel a weak force, and we'll come back to that in a moment. So already quite a while ago, about 40 years ago, in the Homestake mine in South Dakota, and we'll come back to that place later in the talk, an experiment was started by Ray Davis, who wanted to measure neutrinos from the sun, and this is the detector. And the process he was looking for is, so if you remember the beta decay, this is actually just a variant. You put the neutrino in the front, and that is allowed in particle physics. So sometimes it's called inverse beta decay. So you have a neutrino, and you needed something where you had a large probability for this process to happen. So use this material, this liquid, which is actually just cleaning fluid, and almost 400,000 liters of it, which contains chlorine, and you create an argon atom and an electron. This was not an experiment which, as we do it now, extracted the information online as it happens, but what they did, they had the detector run, then they emptied the cleaning fluid, and they looked for argon, and they did this something like once a month. And they did this for many, many years, and these are the measurements. And at some point, people got worried, because this red line, so this is the rate of neutrinos you expect, and these are the years, 1970 to 1994. It turned out that, even if you have large individual uncertainties on this, which are shown by these bars, if you averaged it out, only a third of the neutrinos were arriving here on Earth. Now, that is worrying. Of course, it could be that our model is wrong. It could be that the sun is dying, because actually, it takes a photon, a light particle, 50,000 years to leave the sun. Because it's being rescattered in the sun, it's not transparent. Whereas a neutrino, not doing very much, can actually get out of the sun instantly. And some of you might have watched, there was a science fiction movie about this a few years ago, where some neutrino detector discovered that the sun was dying because of it. Now, don't worry, the sun is perfectly fine, and what is actually happening here, we'll come back to in a second. To explain this, I have to talk a little more about why neutrinos are special. One of the things is that this is, again, the same picture of elementary particles, and the size of the animal you see here corresponds to the relative mass. So from the top quark, which would be like a blue whale, to some other quarks, and the electron and the muon, which is like, the electron is like a squirrel, and this is like a gorilla or a chimpanzee, and of course here at Fermilab, a bison for the tau. And other neutrinos, and this is a bit outdated, so I have to actually put this on top. We now know the neutrinos on this scale are like a fruit fly. Now, that's weird in two ways. First, it's much smaller than the other masses, much, much smaller, but it's also not zero. For a while, we were thinking that the masses are zero. Something I will not talk about, but might have heard about the fact that when the Higgs boson was discovered at CERN a few years ago, that the Higgs is responsible for the mass of elementary particles. We believe now that is not directly true for the neutrinos, and the reason for this is that the mass is so light. The other thing is that because the masses are so small, neutrinos are truly quantum mechanical objects, and it is. We tend to think of particles like little balls or so, which go through space. That's not true when you have an object like this. And this has consequences, because the neutrino particles is actually not what I showed you before, the ones which have the flavor. The neutrino particles, in order for it to be a particle, it has to have a mass. And it turns out that you have to look at the neutrinos in a different way when you talk about them in terms of mass or when you talk about them in terms of what we call flavor. And one is a mixture of the other. And I show this here. So if I look at the neutrino particles, the ones which have mass, small mass, they have different masses, and the size of this splitting of this distance corresponds to the fact that they have how different the masses are. It's on a very small scale. But if I look now at these nu1, nu2, and nu3, which are those three neutrinos, and look at them in terms of the flavor type of neutrinos, they represent mixtures. So like a nu3 is like half of one flavor and half of the other flavor. That is a bit weird, I have to admit, but this is how it works. Now what happens now is if you have a neutrino emitted by the sun, and let's say we emit an electron neutrino, it will also be a mixture of those three mass type neutrinos. And it will travel through space, and because things that are not massless can only travel with less than the speed of light, and it depends how much less on what mass they have, they will travel with a different speed. Now I start with a neutrino here, and then it has these three components with different masses. They go through space, and they actually arrive here. In a simplified picture, they arrive here at a different time, and the mixture has changed, and we suddenly therefore have a different type of neutrino. Another way of thinking about this is to think about them in terms of waves. So I have one neutrino and the other, and they, because they have slightly different mass, are out of phase and have a different velocity. And if I overlay the two, I get this interference pattern, and this corresponds to exactly what we see. One neutrino flavor, let's say the electron neutrino, it oscillates, as we say, to another one in a cyclical pattern like the muon, and then it comes back, and so on and so on. So I hope everyone has understood this. Because if you think you understand quantum mechanics, you don't understand quantum mechanics. Now, if you haven't, just believe me, they oscillate. So when I start with an electron neutrino, something can go, this electron neutrino can become another type of neutrino, and that explained this experiment. And there was another experiment in Canada that proved that actually the reason this is about a third is because the other 2/3 have gone into the two other flavors of neutrino. So the neutrino rate from the sun is fine, but they have just changed their identity like a changeling. Now, something very similar is done in Dune. We start here at Fermilab, and we create our own neutrinos, like the sun. We create our own neutrinos. They go through the Earth and are detected about 1,300 kilometers away in this detector. And what we want, so we start with one flavor, and in this case, because it's easier to make them, it's muon-type neutrinos. We start with 100% of those, and then they change their identity, and at the end, we check how much the identity have changed, and that teaches us a lot about the science. In order to build a project like this, we need 4 ingredients. We need scientists, we need a neutrino beam, a detector, and we need money, okay? Now, this is polite company. I will not talk about the money part. These are the scientists. Dune was formed in 2015 by 2 predecessor projects, one in Europe and one in the US, and now has become a global project. And this global project has countries, of course here is the United States, South America, Europe, and Asia, with more than 1,000 scientists working on Dune from 31 countries, which is 30 real countries, and one is actually CERN, which is an international laboratory in Geneva, which also counts as a country here. Now, how do we make neutrinos? We imitate nature, because there's another source of neutrinos which bombards us all the time. It's from cosmic rays. Cosmic rays are protons that hit the upper atmosphere, produce pions, another particle. They decay into muons, and they decay into neutrinos. This process we can imitate in the lab, and we do this with accelerators under controlled condition here at Fermilab. So we start with protons. They decay into pions. As long as these particles are charged, we can still use electromagnetic forces to kind of steer them. Once they decay then into neutrinos, they actually are gone, and we just can send them in a general direction where our detector is. Now, why do neutrino experiments have to be so big? As you will see in a moment, and the reason is that neutrinos do almost nothing. If you took a neutrino and you took the distance between the sun or the Earth, doesn't matter, to the next neighbor star, which is Alpha or Proxima Centauri, and that is about 1 million times the distance of the Earth to the sun, and you filled it all with water, the neutrino would see a single water molecule. So it is really blind. I mean, again, this is the reason why we don't cry all the time, because all these neutrinos hit us and it doesn't hurt. Yeah? So in order to get anything where we see something from a neutrino interacting with some material, we have to build huge experiments with a lot of stuff in them, and we have to get as many neutrinos as possible. About where we get the neutrinos from, I will not talk in detail. I'll just remind everyone that this is a big part of why Fermilab is the leading lab in accelerator neutrino physics, because it has this unique facility here that allows us to have a very intense neutrino beam. And there is a new program for the next decade, which has just had its ground breaking about 2 weeks ago here. It's called PIP2, Proton Improvement Plan, which will even further increase the intensity of neutrinos we can produce. This is the most complicated plot of the talk, so just bear with me for 30 seconds. So neutrinos oscillate. So we start here with the muon neutrinos, and I said that before. And that means if we go, so this is a distance here, effectively, it's actually distance over the energy of the neutrino. So for like 1 GeV, that's our unit neutrino, that would be 1,000 kilometers. So the muon neutrino disappears, and the other two types start appearing because the sum has to add up, it's a probability, and this goes on and on. There are two frequencies here which are given by the distances, and these frequencies are actually given by the mass difference between these neutrino types, and there are two mass differences, so there are two frequencies. If I want to build an experiment, I want to have this effect maximal. I want to see the maximum amount of oscillation from one flavor to the other. So let's go here. Well, that is where it's maximal, and that is where we have L over E, 500 kilometers. Almost all the blue ones have disappeared, and the red ones are on a peak. If we have a typical energy at Fermilab of 2.5 GeV in these units, doesn't matter exactly what they mean, we can just calculate which length this corresponds to, and this corresponds to 1,300 kilometers. Now, the next step in building the experiment is go to Google Maps and see where you can get from here in 1,300 kilometers, and that is actually in Lead, South Dakota. It takes a little longer here because you don't go, it's almost direct. There happens to be a mine, and that's the same mine we talked about before, the Homestake mine, which was where Ray Davis did a neutrino experiment many years ago, and you can see like neutrinos are coming home. So this is the mine, this is the shaft, this is how the mine looked 240 140 years ago. Gold was found there. It's in the Black Hills in South Dakota. And you can still see that because there's a huge open cut where people dug down just to find the gold, and then they built a mine to go deeper and deeper. And I think the overall depth of the mine is of the order 2 miles. Now, why a mine? Well, first, you know, sometimes, like we had a journalist here filming something for the BBC, and then the first thing they ask, where is the tunnel through which the neutrinos go? There is no tunnel. The neutrinos just go through the Earth. And you could actually go above surface, but there are all these cosmic rays bombarding us, and they really fill your detector with signals you don't want. So you go as deep underground as you can, and this is a mile underground in this mine. And so you built the detector. So this green thing is where we'll build Dune. And this is actually where the Davis experiment I talked about was. There are 2 shafts going down there. This is how it looks down there. It's a mine. And now I will just show you a little bit of a summary how it looks like in this little movie, what I just told you. So this is where we are in the high rise. The beam is produced. The protons are produced in the accelerators here on site. They go through the different acceleration units we have here at Fermilab. Sorry, and so this is a charged particle, yeah? So protons, they can go on a path like this. Then you send them with a slight downward angle into the ground, and you create neutrinos. The neutrinos go through the Earth. You put a detector here. I'll talk about this, why this experiment is actually going to be here at Fermilab. And then the neutrinos go through the Earth, something like 30 miles, and then and then they come out in South Dakota. This is a supernova. We'll come back to the supernova. And this is the detectors. And then things happen, not that often. There's one. And you see a neutrino interacting, producing either electron or muon or something else. The data goes up there. These are zeros and ones, yeah? And then they go out and are analyzed. Good. So you saw these modules. There were 4 of them in the film. And this is where actually the neutrinos are detected. They are filled with liquid argon, and they are pretty big because you need that to see any of the neutrinos. So each of these 4 modules are 60 meters long and about 20 meters high and 20 meters here. So there's like 200 feet. I hope you appreciate that I translate everything into feet online, yeah? And 60 feet and 60 feet. This is liquid argon at a temperature of minus 184 degrees Celsius or minus 300 degrees Fahrenheit. And you have to put that in a cryostat, but fortunately, the technology for that exists. Why? Because we are constantly transporting liquefied gas, natural gas, over the oceans. You would never, gas, to make it efficient, has to be liquefied so it's compact. And the same technology which is used for these kind of ships can be used here to encase the argon and keep it cold. Just to give you a scale, if we take the 4 modules and the liquid argon which is in there, we could fill the inner part of the high rise back there with liquid argon. That is a lot of liquid argon. So there are the 4, so these caverns where each of these 4 detectors will be built, and in the middle we have an extra one which is a service cavern. There is, from the mine, space there, but not enough space to build these detectors, and that has to be excavated. It's a big part of the project. And the way this is done is that the rock comes to the surface and then will be put into this huge hole here, which is the open cut I talked to you about, which was the original part of the mine where people looked for gold. And it's so huge that all the rock we take out, I think, only fills like 1% or so of that hole. Groundbreaking has happened. The typical groundbreaking picture. You can rest assured that none of these people will contribute to the shoveling. So this just shows how it will look, a short movie down there. So there are these 4 detectors. There's the service cavern in the middle. And walk through, and there will be a lot of space here in order to access the caverns. Then you go in. You will have one detector to the right. We look to the right now. And this is where what was in green before, one of the cryostats filled with liquid argon will be located, and then on the other side. And just shows you again the scale of this. It is really huge. And then there will be a service space in between, and then the second cavern, and this will house the utilities in the center. And then there will be space for a third and fourth cavern detector. So how do we find the neutrinos? What do we do actually? So I told you we start with muon neutrinos here, and we want to see, are they still muon neutrinos or have they become electron neutrinos? And there's a simple way to do this. Because they come in pairs, you know if it's an electron type neutrino, it always produces an electron. If it's a muon type neutrino, it always produces a muon. You can even say that's the definition of the game. Yeah? So when I see a neutrino producing a muon, I know it was a muon neutrino. If it produced an electron, I know it's an electron neutrino. And this is exactly what we do. So we have to distinguish the electrons and muons and other particles, and we have to find these. But fortunately, electrons and muons are charged, and that makes it a lot easier. To be fair, nobody has ever seen a neutrino. You can't see a neutrino, because neutrinos, as I said, only interact weakly. The only thing we see is the things they do, they create. And in this case, this is a charged particle. So what happens there? It's actually very simple. There's the big liquid argon volume, and we put a very, very high voltage on it. So you have like 100, 200 kilovolts, and you have an anode and a cathode, very high electric field. The neutrino comes in, creates a charged particle, and the charged particle goes through this argon, and it ionizes the argon. That means it liberates electrons. So it ionizes the argon, which is neutral. It knocks out many, many, many electrons. These electrons are charged, and now they will drift because of this strong electric field to a set of wire planes. So these are just thin wires with a few millimeter distance and in different angles. And they will record the signal. And we do this at different angles. Why at different angles? It's like you have 2 eyes. With 2 eyes, you can reconstruct a 3D image. So by reconstructing the image in 2 or 3 dimensions, we can actually create a 3-dimensional reconstruction of this track. It's actually quite amazing if you think that there's this track, so this particle going through argon, it creates a track which is about 1 millimeter, and then this track drifts. It travels through the argon and for meters, and then we record it as if, you'll see pictures of this. It looks like photographs. That's actually very amazing. Why argon? Well, it's denser than water. That's good, because the more the merrier with neutrinos. The denser it is, the better. Secondly, it's actually relatively cheap and abundant. I know you probably don't need argon in your kitchen, but it's about 1% of the atmosphere. And because there are lots of companies out there that make liquid air, they actually produce argon as a byproduct. The price is actually about $1 a liter, yeah? Or $4 a gallon. So the other advantage is it's actually easy to ionize and also produces a lot of light, which I will not talk about in detail, but is also useful for us. To keep it cold, we need a cryogenic system, so there are lots of piping where the liquid argon is pumped around, cleaned. It has to be really clean. Inside, this is how it will look like. There are basically a volume, a tank filled of argon, and then you have these anodes and cathodes, which create this electric field. And this is all just in very large dimensions. Now, what perhaps we would like to do, but nobody would ever, who gives us money would ever allow us to do, is to just say, that's a great plan, let's build this. Everybody expects us to build a prototype and just make it a little smaller. And so we have actually built quite a few detectors like this at Fermilabs and at other laboratories that work similarly, but are not quite so large. One of them is Microboon, which is here at Fermilab, and this is actually the Microboon cryostat where the liquid argon is hosted, and the experiment is just a few hundred yards over there. And so this is before it went into the detector. It's been running for years, and it produces these, and that's why I mentioned these beautiful pictures. That is what liquid argon detectors can produce. So a caveat, like a lot of pictures, particle physicists and also astronomers show you look like photographs. They are not photographs. These are representations of data. So you have to be a little bit careful, but it's not really like an old bubble chamber picture, which you might have seen, that this is an interpretation of the data as we record it. So the first thing which is wrong, liquid argon is not blue. Yeah? Liquid argon actually looks like water. It's just transparent. It got to be, because otherwise we couldn't see the light in it. The neutrino is coming, this is real data. This is not fake, made up, anything. So this is the invisible neutrino, is coming from the left, and then it interacts and it produces all these tracks here. Now you see actually other stuff going on, and that's because this detector is on the surface. And that means that we get a lot of cosmic rays going through, which we also see. Another recorded event, as we say, this is a muon, a cosmic muon. It stops. And when it stops, it becomes red. What does that mean? Well, that's what we add as a color. So from green to red means it deposits more and more energy. That's very typical when a charged particle goes into somewhere ionized, and then the end of its life, it will deposit most of its energy. It decays into another particle, an electron, and some photons. So it's just beautiful because you see subatomic physics very clearly here. Not the only prototype. We have another one at CERN, which is the International Particle Physics Laboratory, and CERN is a partner on this project. And this is the prototype there. It looks already more like Dune, just a bit smaller. This is about 18 feet times 18 feet. And this is how it looks inside. This is a human. Why does it, this is the cryostat inside. Why is it folded like this? Because of the cold. It has to expand and contract, so you have to do that. And show you, so this is a few pictures just quickly going through. Inside, this is these wire planes, beautiful detectors. This is another prototype, again, from the inside, before the liquid argon, obviously. And another of these detectors, just to show you that this is, they're really, really very, very beautiful. But we then fill them with argon, and this is a picture, and don't worry about the green, that has something to do with taking the photograph. And this photograph shows actually from a camera inside how the liquid argon is being filled in here. So there are like pipes, and so on. You see here the surface of the liquid argon arising. Each of these contains about a few hundred tons of liquid argon. Now, this detector, which we call proto-Dune, has also recorded tracks. And this little movie shows you, again, real data. You see that's where the particles come in, and they produce other particles, and you see that actually there are these tracks going through, and actually most of them have been filtered out. If you look at the whole thing, you see a lot of these cosmics. That is because at any given time there are so many cosmic tracks going through, and that is okay here because we just want to show you that the technology works. But if you want to do real physics, science with it, that's why we have to go deep underground. Again, these cosmic muons come from the sky, and just to give you a feeling, every second and per square meter, about 100 of these charged tracks go through us at any moment. But if you go 1 mile underground, they're all gone. So, back to Dune. What I showed you this picture before, we talked about the FAR detector in South Dakota. This is where we are. There's another detector here. And that's actually quite an important detector, which we absolutely need for this project, because the problem is, what we want to measure is how many of these neutrinos changed their identity. In order to do that, we have to measure how many of these neutrinos are produced here at Fermilab. And that means we also have to put a big neutrino detector here, not quite so big as the one in South Dakota, but big enough, and it will be based on site about 500 meters in this direction, close to Kirk Road. And it will measure the neutrinos before they go to South Dakota, so we know how they look like, and then we can compare. So let me use the last few minutes to talk about something else, which is really one of the primary science goals of the experiment, and that is to understand the role of matter and antimatter. So matter and antimatter goes back to Paul Dirac, a British physicist, who actually wrote this beautiful equation, which you don't have to understand, but it's beautiful, it just looks beautiful, and it predicts there are particles and antiparticles. And actually only 2 years or 3 years later, C.D. Anderson in cosmic rays actually discovered the partner of the electron, which is the positron, and this is the first positron ever seen. It goes from here to here. Now, the problem with matter and antimatter is that we assume that the Big Bang produced equal amounts of matter and antimatter. So like, well, there wasn't an Earth then, but an Earth and an anti-Earth. The problem, however, is that over time, antimatter disappeared, and what's left over is only matter, obviously, in our observable universe. You only need a small asymmetry between matter and antimatter to be able to do that, but it is quite a strange effect which we haven't really understood. And the buzzword, so if you want to impress what you learned here, is here to understand CP violation. So what does this mean? CP violation goes back to, this is Mr. Sakharov, a famous physicist. He, Russian physicist, he postulated that one of the conditions for the universe to be in an asymmetric state is that a symmetry which we call CP is being violated. In order to have, as we see here, a universe which at all scales we know is dominated by matter. And so what does CP mean? Well, it's actually not that difficult. When you go from a particle to an antiparticle, you go from an electron to a positron, for example. So what you do, you turn around the charge from a negative to a positive charge. That's where the C comes from. And the P means parity, because the electron actually is like a spin. It spins, and you turn around that spin, we say it goes from left-handed to right-handed. And when you do that, then you get from particle to antiparticle. So CP actually means nothing else than making an antiparticle out of a particle. Now, with Dune, what we want to do is to study exactly that. And the way we can do this is by selecting the type of neutrinos here. And selecting the type of neutrinos we can do because actually in our beam, we have the option to choose the charge. So we choose the charge, either a positively charged pion or a negatively charged pion. And then we know that's the same C, like you go from pi minus to pi plus, from particle to antiparticle. And if we do both, and we do this for several years, we run in this mode for a few years and this mode for years, we compare the results, we can tell you whether CP, whether we get exactly the same result or whether CP, as we say, is violated. So these are some of the questions Dune can answer. And I haven't talked really about the first one, but the important one here is, do neutrinos violate CP symmetry, and can possibly thereby contribute to explaining why we have a matter-dominated universe? Other questions: is it actually only 3 neutrinos? How do we know that? Could there be fourth ones? That's the thing we can also study. And of course, perhaps the most interesting bit for any scientist, are there stuff which we haven't found yet? New and unexpected stuff. I'm a bit over time, but this is good, so I'll just... Another thing we can do is this. So no, we can't make a star explode, but this is actually an animation. Yeah, animation of the supernova that happened in the year 1054. We know this because it was actually recorded by Chinese scientists at the time. And supernova are star explosions, and these star explosions they work basically, there are different types, but the ones we are interested in according to a certain pattern, where when the star runs out of fuel, it starts to collapse. The gravitational energy, like I have a ball and I let it drop, there's gravitational energy which is transformed into kinetic energy when I drop it. In the same way, when the star collapses, I have to transform this potential energy, or gravitational energy, to kinetic energy. And this kinetic energy is so vast, it has to be emitted somehow. And what many people don't realize is, because what happens when the protons and the electrons get squished together in this process, you create neutrons, a neutron star, and actually, because again, this is almost like the beta decay we had at the beginning, there's a neutrino. 99% of the energy of a supernova is carried away by neutrinos, which is actually quite amazing. 1987, there was a supernova in the Large Magellanic Cloud, and there were smaller neutrino detectors online at the time, and they actually saw 23 neutrinos within a time of about 10 seconds. That's the time in which this supernova happens. With Dune, if we can actually see a supernova, which is not too far away, not too close either, please, then we will see thousands of neutrinos within 10 seconds. This will give us enormous information about neutrinos and about supernovae, which are one of the most violent events in the universe. So let me wrap up with 2 or 3 slides which just shows you that we are not alone. This is great physics. If you do great physics, you have competitors. This is us. There's a competitor experiment in Japan, and this is called Hyperkamiokande and Superkamiokande, but this is Hyperkamiokande is still in the planning stage. And then there's also a similar experiment, which is not really a competitor because it doesn't use beam neutrinos, on the South Pole. These experiments work differently. They work with water. Water has a lot of advantages. One of them is that it's abundant. You can build huge detectors. The disadvantage of water is that the reconstruction, those beautiful pictures I've shown you, that's not possible with a water detector. I will just flash through these few slides so that we have some time for discussion, and I can talk about these detectors too, but let me summarize what I hope I have convinced you of. DUNE is ahead of its competition and is expected to break new ground in understanding of neutrinos and their role in the universe. It is the largest international science project on US soil, or actually under US soil to be more precise, and a global project with more than 1,000 scientists from 31 countries. Together with DUNE, there is another project which we call LBNF. That's the facility that is extremely important. It provides us with the neutrinos and the excavation. The physicists built the detector, but there's a lot of stuff going around it. And this is important because it actually makes Fermilab the ideal place to do this physics, because it has the world's highest intensity neutrino beam, and this facility provides the necessary infrastructure to do the discovery science we want to do. DUNE and also LBNF will bring benefits, and I think this is something we always have to stress because it is important to not only the global science community, but also to the local communities, in this case here around Fermilab, and of course in South Dakotas, and this will continue to be the case for several decades. The timeline of DUNE is roughly like this, and of course this is still developing. We are currently in the prototyping stage and planning stage. I showed you that, and these prototypes are working perfectly. It's really, really very exciting with such a challenging technology. The far side, we have to start very soon to physically excavate the caverns for putting the detectors, and then in about 5 years we'll start installing the detectors, and a few years later we will have the beam available from Fermilab. And then this is a science program which will go on for at least a decade. I'm pretty sure it will actually be significantly longer, and it will make this lab the prime lab for doing neutrino physics with accelerators for the next generation. And I hope there's some younger, I can't see anyone, by the way. It's this odd effect of, because I'm in the light. So if you are a high school student or a student, you do your degree, you become a scientist at Fermilab. That's the experiment where you will do your research. So let me thank you for the attention, for coming here tonight, for listening to this. I hope I could convey a little bit the excitement we all have about this project.